Maybe you will recall, we've been looking at the interval of convergence for power series. We're trying to figure out what values of x we can plug into a power series and get a convergent series. That's the idea. We want to be able to plug things into this function and see what makes sense. And in this context, getting something that makes sense means a convergent series. If I plug 5 into this series, do I get a convergent series? If I plug -2 into the series, do we get a convergent series? That's the question. What can we plug into this series, this power series? And yesterday, I gave some vague instruction on this that we will hopefully make a little less vague today. And I said, think about the ratio test. The reason that we like the ratio test, first of all, it gives us absolute convergence, which is awesome. That's our favorite kind of convergence. And second of all, it gives us a very straightforward thing to do that says if this limit is less than 1, then you get absolute convergence. It doesn't tell us what's going on if this limit is equal to 1. But we're going to see that that doesn't make very much difference here. So we're going to do a ratio test. Yesterday, we just wanted to think about this. Today, we're going to actually write down a ratio test. And then we're going to think of strategies to avoid writing down the ratio test all the time. Because it's a lot of writing. We're mathematicians. We're kind of lazy. We don't want to have to write everything all the time. That's why we invented algebra, so that our Pythagorean theorem could be like, well, a squared plus b squared equals c squared. And then we spread that information around enough that everybody knows that c is a hypotenuse. So we don't have to be like, all the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse, just to say that a squared plus b squared equals c squared. Make sense? All right. So we're just trying to spread mathematical culture around so we can get away with stuff like that. We can think of lines as y equals mx plus b. But anybody out of high school would be like, oh, y equals, like if you're spies or something like that. It'd be terrible because everybody knows y equals and then mx plus b. Can't use that one. All right. So what we're going to be looking for, remember that in a ratio test, we're looking for 3 things. We're looking at categorize 3 kinds of factors. Factorials on top, in the middle are exponentials, and our polynomials that the ratio test is going to ignore. Our power series always has this exponential-like factor in it. Because when I plug in a value for x, x minus a, that's just a constant. So we've always got this exponential. So the ratio test will care about this x minus a to the n part, because that's exponential in n. It's polynomial in x, it's exponential in n. So then we just have to look at what's going on in the Cn. Remember those 3 things that we're looking for: factorials, exponentials, polynomial, numerator, denominator. That's what the ratio test is looking at. So let's do a ratio test. We'll take the limit as n goes to infinity of the absolute value of Cn plus 1, whatever that may look like, x minus a to the n plus 1 over Cn x minus a to the n. Cn, that could be anything. We don't know what's going on there, but we do know what's going on in this x minus a to the n plus 1 over x minus a to the n. That's going to act like the exponential stuff in a ratio test. I've got 1 power higher on top, so n plus 1 on the top divided by n on the bottom. That will leave 1 behind. X, if we got to the 10th on top and to the 9th on the bottom, we'll be left with to the 1st. We add to the 50th on top, to the 49th on the bottom, we'll end up to the 1st. So when we simplify, x minus a to the n plus 1 over x minus a to the n. I was coming out in purple before. When we cancel out the x minus a to the n, the x minus a no longer has anything to do with n. And so we could factor it out. So if we cancel a bunch of x minus a, we're left with one factor of x minus a that no longer has anything to do with n, so we can factor it out of the limit as n goes to infinity. Then we get the power of the ratio test. If this limit is less than 1, then the series is absolutely convergent. Oh, I shouldn't put exclamation points. We can't shout anything anymore in math class, because now that we know it means factorial. So what the ratio test is giving us is an interval where the power series converges. And it's going to depend on what's going on with this limit. There are three things that can happen with this limit that we care about. So if we look at the limit as n goes to infinity, the absolute value of Cn plus 1 over Cn, just pulling out the coefficients. If that limit is equal to 0, then it doesn't matter what we have for x minus a. The limit from the ratio test is 0. And regardless of the value of x, the power series converges. If that limit is equal to 0, then the power series will converge for all x, because the limit from the ratio test will be equal to 0, regardless of the value of x that we pick. Remember what we're trying to do. What value of x do we get a convergent series? If this limit goes to infinity, then the power series only converges when x equals a. So if the limit as n goes to infinity of that Cn plus 1 over Cn, if that part is going to infinity, then the only way to get the limit from the power series to be less than 1 is to by plugging in a, which makes this factor 0. So I have 0 times this large number. That will be equal to 0. So the power series only converges when x equals a. Those are the two extremes. We got 0 on one side, that limit is 0. Power series converges for all x. That limit goes to infinity, that power series only converges when x equals a. And then in the middle, that limit could be some finite value. And we can describe the interval of convergence as the absolute value of x minus a is less than 1 over L. If that limit is equal to some value just called L, we want to know an interval, divide by L. These are the three things that can happen. We're looking at the limit. We're looking at the ratio test on just the coefficients. That limit can either be 0, infinity, or some finite amount. Draw a picture of let's draw a picture of the absolute value of x minus a is less than 1 over L. Another way to read the absolute value of x minus a less than 1 over L is to say everything within 1 over L units of a. That's how I want to read this absolute value inequality. This is going to be everything within 1 over L units of a. A is in the middle, and we have this radius of 1 over L on either side of it. Going to be everything within 1 over L units of a. So what this is going to look like is we have a in the middle. And I go 1 over L units above and 1 over L units below. So it's a plus or minus 1 over L. This 1 over L, we will call the radius of convergence because it's the radius of our interval of convergence. The center of our interval is A. And the radius is 1 over L. But when we see this absolute value inequality, absolute x minus a less than 1 over L, we want to start interpreting that as everything within 1 over L units of a. The difference between x and a is less than 1 over L. That's what subtraction is. Subtraction is the difference, the distance between X and A, positive or negative. Absolute X minus A less than 1 over L is everything within 1 over L units of A. A is in the middle. We go 1 over L units above, 1 over L units below. This exactly matches with how we would solve this absolute value inequality. If I have this absolute value, when we solve an absolute value inequality of this less than type, to get rid of the absolute values, I say that X minus A is less than 1 over L and greater than minus 1 over L. Then I can add A through the inequality. There's the top end at A plus 1 over L, and here's the bottom end at A minus 1 over L. Recall that the ratio test is blind to things like polynomials and radicals. If the limit from the ratio test is equal to 1, then the ratio test does not know what's going on. So we have to look at the endpoints of our interval of convergence separately, because the ratio test does not know what's happening at the endpoints. So the ratio test is inconclusive at the endpoints of the interval of convergence. The ratio test is inconclusive at the endpoints of the interval of convergence. So we have to check those separately with some other test. Pause for copying. I don't need to read that part of the teleprompter. I'm only hallucinating the teleprompter. I've learned long ago not to read anything off the teleprompter. If you had a teacher that was a main character in a horror movie, that would be maybe, I think that's what the spirit following it would be. So I'd be haunted by like a teleprompter, always trying to get me to read that. When it first manifests itself, I'd be like sitting in class and the audience would see a teleprompter and it looked like I'm just reading off the teleprompter. It's like right here, by the way. So I'm just like all talking, it's like, and so we see that there are 3 things, and I keep looking at the teleprompter, 3 possibilities for interval of convergence. And then it would say something horrible on it, and I would stop start reading the sentence. And all of your families are, and then I would read it, and the audience would be like, oh, but the class would be like, oh, what's going on with Professor Lee? Then you'd be like, oh, well, he told us that he hallucinates the teleprompter, because most horror movies could be solved with like communication. Like Game of Thrones plus cell phones. Game of Thrones just doesn't happen if everybody got cell phones. Someone be like, I thought all the Targaryens were dead. And they go, yeah, obviously. It's like, oh, well, then who's this person posting on the Instagram? You know what I mean? I'm sorry. Collectively, we have banished Game of Thrones. I forgot about that. Season 8 happened. Has anything ever left the collective consciousness so quickly when it was so pervasive? I mean, they had people naming their kids after Game of Thrones characters. And now Game of Thrones is gone. And not just faded out of existence. It's like, I think we have banished it. Like some things will just fade out of existence, right? But there are other things that we collectively banish. And I think Game of Thrones got banished. Duran, we just kind of forgot about. Then they show up every once in a while. It's like, oh yeah. But if Game of Thrones showed back up, we'd be like, oh, ugh. Behind me, Game of Thrones. You know what I mean? What are we talking about? Oh, yes. See, that's what happens when I read the teleprompter. There are three things that can happen with our interval of convergence. It's always going to look like a middle with some space around it. It could just be the middle with a radius of 0. If the limit is infinity, then the power series only converges at the center. We don't get any of the stuff on the sides. We have to zero out all the terms to get this power series to converge. That's the nuclear option. Zero out the terms. Guaranteed convergence. We could have some finite radius about the center, but it's always balanced, the same distance above and below. Or we could take that radius of convergence and go to infinity, where we just cover everything. Questions? Yeah. Oh, that just means L is some finite. It's just some finite amount. So we can have 0, some finite amount, or infinity. Those are the three choices. The endpoints are 0 and infinity, and in the middle, we've got something finite. Questions? Let's begin death by examples. Let's start with our most basic power series, X. Kind of silly, let's see. Oh, X to the n, sorry. There's got to be an n somewhere. In this case, the Cn is just 1 for all n. I'm starting with the most simple. constant coefficient. Power series. The question with the power series is, what is the interval of convergence? We know that to find the interval of convergence, we run a ratio test. So let's run some ratio tests until that time appears where we don't have to do the ratio test anymore. We can just see what's going to happen. We'll take the limit as n goes to infinity of the absolute value of Cn plus 1 over Cn What's always going to happen when we apply the ratio test to a power series is that the x part will cancel out and be able to escape the limit. That leaves behind the limit as n goes to infinity of 1. And as n goes to infinity, 1 is just always 1. So the limit from the ratio test is absolute value of x. Then we have to remember what we're doing. We're doing a ratio test. And the ratio test says stuff converges if the limit from the ratio test, in this case, absolute value of x, is less than 1. This is with everything within 1 unit of 0. Zero in the middle, 1 unit above, and 1 unit below. The ratio test says everything strictly within 1 unit of 0 will give us convergence. Because if x is equal to 1/2, the absolute value of 1/2 is 1/2, which is less than 1. This power series will converge at 1/2. It also converges at negative 1/2. At x equals negative 1/2, the absolute value of negative 1/2 is 1/2, which is less than 1, converges. If x is equal to 3, way up here, the limit from the ratio test is greater than 1, and so the series diverges. If x is equal to negative 3, the interval from the limit from the ratio test is 3, which is greater than 1, so the series diverges. So here, all the stuff in between this power series converges. But what about 1 and negative 1? When x is equal to 1, the power series diverges because it's 1 plus 1 plus 1 plus 1 plus 1. When x is equal to negative 1, the power series also diverges. Remember your test for convergence. Also remember that at the endpoints of your interval of convergence, you have to do something other than the ratio test. So if we look at this sum as n goes from 0 to infinity of -1 to the n, if we take the limit as n goes to infinity, that limit does not exist. For large values of n, we'll either have 0 or 1. We're not getting closer to any particular value. We can never be within epsilon of some limit. What's that? A is equal to 0 because it's just an x. So we're reading this x as x minus 0. That's what's in the middle. Oops, that's what's in the middle. It is super important that you look at that sum, 1 minus 1 plus 1 minus 1 plus 1 minus 1, and recognize that that is not going to be 1 or 0. That limit doesn't exist. So this sum is not some finite amount. Perfect. Any questions? So both endpoints, neither endpoint is included in the interval of convergence. So 1 and -1 are not included. So I can just write this as absolute value of x is strictly less than 1. Neither endpoint is included in the interval. Let's change a little bit. Let's move our power series. Let's move the center of our power series to 4. The center of the power series, that's where we know it will always converge. If I plug x equals 4 into this power series, I get a bunch of zeros. I get convergence. This is the nuclear option. We zero out all the terms. Zero out all the terms, and we'll get convergence. But what else will we get? Will it only be 4? Will it be some finite radius about 4? Or will it be an infinite radius about 4? To find out, we run a ratio test. In this problem, the same thing happened as in the previous problem. X minus 4 to the n plus 1 divided by x minus 4 to the n will leave behind one factor of x minus 4. Since it no longer involves n, we can factor it out of the limit. That leaves behind just a 1. The limit as n goes to infinity of 1 is 1. So the limit from the ratio test is equal to absolute x minus 4. Same place we were up here with x. This is the limit . The ratio test gives us absolute convergence when the limit from the ratio test is less than 1. When we write the absolute value of x minus 4 is less than 1, we're saying everything within 1 unit of 4. 4 is in the middle. 4 plus 1 is 5. 4 minus 1 is 3. We definitely get everything strictly between 3 and 5. We've got to check the endpoints. The endpoints are x equals 5 and 3. I have to plug them into our power series. If x is 5, I get 5 minus 4, which is 1. So if x is equal to 5, this power series diverges when x is equal to 5. Just like what happened in the first one. I plugged in that bigger endpoint. I plugged in the right endpoint, and I just got 1 to the n. If I plug in the left endpoint, my power series diverges. Because the power series looks like 1 minus 1 plus 1 minus 1 plus 1 minus 1. And that, in there, the terms have no limit. The limit doesn't exist. So the power series, or the series, diverges. Neither endpoint is included. So we get everything strictly between 3 and 5. 3 is not included, 5 is not included. Tomorrow, we'll pick up with, we're using these two as a base. Here's the summary of tomorrow. Polynomials about the endpoints. Exponential. We'll adjust the finite radius and factorial. That'll give us a chance at a radius of 0 or infinity. Unless we carefully balance out the factorial, it's a very contrived example. Which, being a math class, of course we do. Because we like outliers to have an outsized piece of every student's mind. Like factoring polynomials. Most polynomials are factorable. Most of the polynomials I run into, they've been factorable. But most of the polynomials you run out into the wild at random are not going to be factored. You've got this skewed view because of how you were raised. You have been programmed to think that most polynomials are factorable by your experience, a curated experience. You were programmed with a bias towards polynomials. All right, that's going to be it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.